Hi everyone, my name is Barber, and this is my Physics 106 final video project. So we're going to be talking today about ferromagnets and electromagnets, so let's just dive right in here. So first off, we need to know the basics, obviously, what is magnetism? We know that magnetism is a force which is driven by electric current and charges. And so these three variables here, force, current, and charges, are directly correlated with each other. And so I just put a picture here, two magnets interacting. Each of them has a north and a south pole. We know that each magnet has a north and a south pole. This is also known as their positive and negative sides. And we know that like poles repel, such as positive and negative, and that opposite poles attract each other, like positive to negative always. And no matter what, the poles cannot be isolated, meaning that a magnet cannot just be broken into a north pole or just a south pole. Whenever you break a magnet, it's always going to come in a pair. And so the two types of magnet, like I said before, are going to be the ferromagnets and the electromagnets. And the ferromagnet is just a normal kind of magnet we see here, everyday magnet. And electromagnets are magnets powered by an electrical source. Just put a picture here of a battery powering a wire. And I'm going to be doing some experiments today showing you how those work. So let's just dive right into that as well. Okay, so first we're going to talk about electromagnets. So electromagnets are basically magnets with electric current running through them. So they depend on electric currents to make their magnetic fields. And they create forces on moving charges, and these kinds of forces are known as Lorentz forces. And you can calculate the magnetic force using the following equation, which is F equals QVB times sine theta, where F is the force, Q is the electric charge, V is the velocity of the charge, or the velocity of how fast the object's going, B is the magnetic field strength, and theta is the angle less than 180 degrees between the velocity vector and the magnetic field vector. So what I did is I made an experiment using battery, neodymium magnets, and copper wire. And it's going to demonstrate exactly how these electromagnets kind of work here. So let's just watch this video. I put it in slow-mo so you all can see exactly what's happening. So I put the battery in with two neodymium magnets attached on each side. There's actually 4 attached on both sides. So we're just going to watch that again. And what happens is this battery's charge is being conducted throughout the copper coil, from the magnets to the copper coil. And it's creating a magnetic field, which is causing this battery to move through. And we could use the Lorentz force here. Talking about the battery, we could find the force using the charge of the battery, the velocity. We could measure the velocity of how fast this battery is traveling. And we could use a magnetometer to find the strength of the magnetic field. And we could use the angle of the magnetic field, which is just tangential to the velocity vector. And so, we could find all of that if we needed to. So that's just a little real-life application there of how that works. So to dive into ferromagnets here, these are just your typical kind of magnets you think about when you think about magnets. And the clear definition here is ferromagnets are objects that have intrinsic magnetic properties. So, for example, ferromagnet, the root of ferro actually means iron. So iron is one of those objects that has intrinsic magnetic properties. And we see here's an example. And the interesting thing about ferromagnets is each atom inside a ferromagnet acts like a little tiny magnet itself. And we can see here, there's a little demonstration picture. So we see that these domains in each atom are all randomly oriented. And that's why in a ferromagnet, it doesn't actually just move, because there's no direction that these are all moving towards. So the object itself isn't going to move. But once a ferromagnet interacts with another ferromagnet or a electromagnetic magnet, all the poles are going to be directing to attract towards the other magnet's respective poles. Okay, so to explain ferromagnetism a little bit better, I designed another experiment. I went out and bought some ferromagnetic putty, so I made a little video here. So in the video, you can see that this putty I have is a magnetic thinking putty, and what we do is we take it out, and you can see it's looks a lot like silly putty. The difference is it has magnetic type material embedded within it, and so I'm just showing you here a little bit what it looks like. And what we're going to do here is we're going to put it back in the jar. I put a neodymium magnet inside, and we're going to watch as the randomly oriented poles within the ferromagnetic putty are going to align with the neodymium magnet. I apologize for the lag here. I'm not sure why that does that sometimes. But this is the before video, so you're going to see a little bit of movement, but not much. And afterwards, you're going to see it's going to be like a time lapse of about 20 minutes or so. And you're going to see the change. So let's go to this video. Okay, so you see now the ferromagnetic putty, the poles, the randomly oriented poles within the ferromagnetic putty have oriented themselves in a way so that they are attracted towards the neodymium magnets. And you can just see like almost like a liquid. It's like each little particle is trying to move towards those neodymium magnets. Alright, so that's the end of my video here. Let me know how you thought I did in the peer reviews here, and I hope you guys learned a little bit more about magnets.